All right, today we're going to review sequence series. And don't be alarmed by these phrases, exponential functions. We are dealing with exponential functions when we deal with those. And we'll also see a term, recursive formula, that you're not familiar with. But again, don't panic. These all go hand in hand. It's just a little verbiage difference. Let's do one thing before we get started. Make sure you've got a calculator handy. We're going to be doing series and sequence, both of which require a lot of work. But let's talk about our different formulas, our arithmetic formula. Remember, our formula for arithmetic is noted a sub n. And the way that we calculate our formula is a sub 1, the first term in the sequence, plus the common difference, d, times n minus 1. Remember, if we're doing a sequence, we are going to actually put in an n value. If we're doing a series, we will be using the variable and let the calculator do that for us. And then the second type is a geometric. So in our geometric sequence, our formula again is a sub n equals a sub 1 times our common ratio, which is denoted with an r to the n minus 1 power. So we're going to have to do a little recollection and a little thinking on these as well as we go through, because we're going to have some application, and it's very important when we do these applications that we are dealing with appropriate time. So those are our two formulas. Hopefully you have those handy. Hopefully you have a calculator handy now. So this sheet is posted for you on Canvas. We're going to read the instructions, and I'm going to zoom in a little bit so we can see these a little better. We're going to determine whether each sequence is arithmetic, geometric, or neither. Determine the explicit formula. That would be the a sub n. And then we're going to find the 11th term in a sequence. Remember, we don't even have to say that. That's what the a stands for. And then the 11th term in a series. That's what the s stands for. All right, let's just go right down the row and establish what we have on all of these. Remember, arithmetic is when we have a common difference, that is an adding or subtracting pattern. And a common ratio is when we have a dividing or multiplying pattern. So let's just go down through and see what we have here. We see we go from -2 to -6. Well, that would be a pattern of -4. -4 does not take us to -18, so this is not arithmetic. So the next thing we're going to do is check if it's a geometric. And remember, what we do on a geometric is all we have to do is divide this term by that term. And then we will have the common ratio. We can do this one in our head, though. We are going from 2 to 6. That is a common ratio of times 3. So the pattern stays true as we move on. Times 3 gets us to 18, and times 3 gets us to 54. So this is a geometric sequence. Let's go ahead and just finish out all of these. Letter B, excuse me. We subtract 4 to get to -6, which rings true to the next one, which rings true to the next one. So we have a arithmetic for this one. We've got an arithmetic sequence for this one. Moving to the next one, we see this would be a subtraction of 4, and then a subtraction of 2, and then a subtraction of 8. We didn't even have to check the third one because as soon as it fails, it fails. All right, so this is not an arithmetic, so we're going to see if it's a geometric. 6 divided by 2 is 3, and 8 divided by 6 is not 3. That's all that matters. So this is neither. This is neither arithmetic or geometric. All right, and then the letter D. On the letter D, what we're going to see is to go from 10 to 5 is a -5, which is not what happens to go from here to here. So it's not arithmetic. To go from 5 to 10, remember we take the second term divided by the first term. That would be 5 divided by 10, which is 1/2. 1/2 of 5 is in fact 2.5, and 1/2 of 2.5 is 1.5. So our fourth one is geometric. All right, so we've identified what we have on all of these terms. We're done with C. So now we're going to identify the different parts. Remember, in our formula, we need an a sub n, or excuse me, the formula is a sub n. We need an a sub 1, and in this one, we need a common ratio. On letter B, we need an a sub 1, the starting point, and we need a common difference. Letter C is finished. And letter D, in order to write the equation, we need the first term, and we need the common ratio. Now, we've already got all of these things. They're listed. Remember, a sub 1 is the first term in the sequence. So the first term in the first two is the same. We have a first term of -2 and -2. Jumping down to D, we have a first term of 10. Now we're going to put our common ratios. Well, we saw that this one had a common ratio of 3. Letter B had a common difference of -4. And letter D had a common ratio of 1/2. So at this point, we need to know our formulas. We need to know our formulas like we wrote on the first page, and we need to identify which one we are using. So on letter A, we're using the geometric. And if you remember, the geometric formula said a sub 1, that would be -2 in this case, times the common ratio, which is 3, to the n minus 1 power. So there's our formula for letter A. For a arithmetic, it was the first term. Now it's plus the common difference. Well, in this case, we're going to go plus a negative. So instead, we could say -4 times n minus 1. And then we're going to write the other equation, but I want to highlight something that is a very common mistake I do not want you to make dealing with this. But let's finish this out. We have a starting value of 10. We have a common ratio of 1/2. You could have put 0.5 as well. Calculator doesn't care. And then n minus 1. Remember, the n minus 1's purpose is to adjust our sequence because we are not starting our counting at 0. So our formula needs this adjustment. Now let's talk back at letter B real fast. On B, the point I wanted to highlight was this. Do not come in here and say -2 minus 4 equals -6. This is a huge no-no. This is another thing you will see on your ACT from time to time because they know that people do this. We're doing math. We're not reading. Reading is left to right, top to bottom. Remember, in math, we have an order of operation that we have to follow, and the order of operation does not start with adding or subtracting. It starts preceding that is multiplication. So make sure that we do not do this. Now, we are going to rely a lot on our calculators here. So doesn't want to move. So we got a little more useful things here. So what we're going to do is we're actually going to take these to the calculator. I'll explain what we're doing. I'll try to post a video that reminds you how we put these in the calculator, but let's first talk about what they want from us. They want the 11th term in the sequence. And again, the way they tell us that is just simply saying a sub 11. And they want the series, which is a sub or s sub 11. So when I go to my calculator, what I'm going to put in is exactly what it reads. We're going to go to this formula, and in place of my n, I'm going to plug in an 11. So it's going to be -2 times 3 to the 11 minus 1 power. And we'll go ahead and do this summation thing as well. Remember, the summation is where we have to use our calculator, alpha F2. And the second option is the summation sign. Summation sign looks like this. And And we are going from the first term in the sequence, so we put the 1 there, to the 11th term in the sequence. And then after that, this is our rule or our explicit formula. You'll see both of those phrases, but our explicit formula is what we wrote here. So our explicit formula, -2 times 3, and then we'll need to use the letter X. Our calculator doesn't understand N. Those of you that have a calculator that produces a parentheses, make sure you do not adjust their parentheses. Yours will need to look like this. Most of you are using a TI-84, so it's going to look exactly like it reads. At this point, it's in my calculator's hand. So what I'm going to do is pause it, put these values in, and see what comes out. So coming out of the first A sub 11 question is the value -118,098. And coming out from the sequence of the same value is going to be -177,146. 177,000, -177,146. All right, let's move to the next ones. We'll write all of these out and we'll take them all to the calculator. How about that? A sub 11. Again, this one we put directly as it reads. So let's zoom in here. This one is going to be -2 minus 4, 11 minus 1. And S sub 11 is going to be the summation of first to 11th term. And then we just put in our rule, and this is the part where we do actually put in our variable. Do not put in an N. Your calculator doesn't understand that. So these are the parts that we should be putting into our calculator here. And I'm going to pause it, put those into my calculator, and see what comes out of those answers. So I did take these to my calculator, and as I was doing this, I was reminded of something that I think we need to address. Make sure that you do not put in subtraction signs when negatives are required. So when we find the 11th term in this sequence, it would be -42. And the series, that's the adding up of the first 11 terms, we get -242. And we'll move to the last one here. Give you all a second to get that down. All right, so somewhere in all my graphics there, I lost some information. We're just going to copy this down. The starting value was 10. The common ratio was 1/2. We see our explicit formula there. So again, A sub 11 is going to be an equation with 11 plugged in. And our series will be the same thing, except for we will be using our summation formula. First term in the sequence to the 11th. And guys, we just kind of keyed in on the 11th term today. Don't think that 11 is anything special. It's just what we decided to do. All right, I'm going to take this to my calculator, bring back some answers. So in this problem, we get to exercise another skill we need to be reminded of. First off, when we do this, we come out with some really weird fractions. I'm not even going to put them. I will say them. They're 0.009765, blah, 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 blah. Keeps going for a while. Remember, 2-button sequence. Actually, 3, sorry. I guess it's 2 buttons. You just got to hit 1 twice. Math, enter, twice. And that will change your decimal into a fraction. And when I do that, my calculator tells me that this is 5 over 512. And my series, when I put this in my calculator, ends up being just under 20, 19.990, blah, 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 blah. I again hit math, enter, enter. And what I learn is it is 10,235 over 512. Again, I wish I could take credit for this fraction work, but it's not me, it's my calculator. Remember, math, enter, enter. All right, so that's our series and sequence. That's kind of the heart of it. That's what I hope you're the best at. We're going to put some application on some word problems, and we're going to talk about some recursive things. All right, here's the recursive thing. What a recursive formula is just simply building off of the previous answer. We talk about Fibonacci's pattern. Remember 1, 1, 1, 1, 1, 2, 1, 1, 2, 3. It's building off the previous one. It was the sum of the other two. That is a form of a recursive formula. But a recursive formula is simply known with this statement, a sub n minus 1. Now this does get a little bit confusing because we use the power n minus 1 all the time, but this is not a power, this is a subscript. What this subscript term means is the last answer. So if we're on the 23rd number in the sequence, this means plug in the 22nd because we're building off of the previous term's sequence. Geometric do this in their own fashion. But if you ever see the word recursive, that just means build off of the last one. So if we're looking again, 27th term, well, that means you have to know the 26th in order to find the 27th because the 27th is all dependent on the 26th. All right, these formulas can be geometric and they can be explicit. On this particular matching one, all we really need to do is plug in our values to these equations and see which one actually works. Here's what I mean. If a sub 1 is 5, when I plug in 1 to any of these equations, the result should be 5. So just take the first one, for instance. I know the first one is wrong, but if I said a sub 1 into this equation, and then we write the equation, negative 3n plus 7, well, this tells me the a sub 1 is supposed to be 5. So when I plug in the number 1, because remember we replaced n with 1, so we've got to do it on both sides, we see that this ends up being negative 3 plus 7, which is not 5. So this does not work for the first equation. But we don't want to just arbitrarily throw these things in. Let's use our common sense on these and see what's happening to these numbers. Remember, geometric is a multiplication pattern, and arithmetic is an adding or subtracting. It's an arithmetic pattern. All right, so let's take a look at that. Number one, there are other ways of doing this, but you know me, I like to use common sense and just practical thinking. So I see that this value here has a base of 2. That means the equation is doubling every time. Now know this, the doubling part is not this. Remember, the value in front is where we started from. This one is not where we started from. This is the amount we're changing, and that would be our base here. So now if you're looking this and you're saying, well, isn't a sub 1 supposed to be 5? Well, we'll talk about that in just a second, but let's just see if it actually works. If we're talking about a sub 1 into our equation, that means we are going to plug in the number 1. And when we do this, the result should be 5. So remember our order of operations, 2 to the 1 power is 2. and 2 times 5/2 is in fact 5. That doesn't mean that this is the correct answer. Other equations and other sequences could do that, but this is the one that works. Let's talk about this though. Why is it 5/2 instead of, and that is our correct answer, the letter A matches with pattern 3. Pattern 3 there. Why is it 5/2? Why is it 5/2? Remember, my pattern is doubling. Well, the reason why it's 5/2 is all to do with our exponent. Our exponent is supposed to say -1, but this one does not. So this one is not starting at the first term in the sequence. It's starting at the 0th term, the one before the first, which I understand there's no such word, but hopefully you understand my meaning. So what we essentially have to do to understand this equation is to back up a step. And since this step is actually doubling, backing up a step would be taking half. And half of 5 is in fact 5/2. So that's why that one looks the way it does. Look at pattern I here. It also does not have an I -1, so we're going to have to adjust for that as well. All right, so this is the third one, goes with letter A. If we're looking at this one again, common sense should tell us that this is a -3. That's a linear pattern. Means it's arithmetic. Well, this formula right here is a geometric. So it's clearly not that one. The only one left's the one at the top, because it does have a linear pattern, excuse me. Let's talk and see if it works. Remember, if we plug in a sub 1, 4 is supposed to come out. And we've actually already done this one, haven't we? -3 plus 7 is in fact 4, so this pattern does work for number 1. Why doesn't the pattern look like the other one? They've just distributed it, and they've also backed up a step. This is not n minus 1. This is the normal n. The only thing left is the second pattern. Let's just plug this in and see if it works. If we plug in 2 to our equation, what should come out, a sub 1 we should plug in, and 2 should come out. So if we plug in 1, remember anything to the 0 power is 1. So what we end up with essentially is 2 times 1, because 3 to the 0 power equals 1. So 2 times 1 is in fact 2. That would be my suggestion as you work through your recursive formulas, is just plug in and see which equations actually work. Be very conscious of this. Sometimes you may need to plug in more than one. All right, now we have some big application questions. These are where these actually are used in life. Pay close attention. It's actually not really hard if you stick to those formulas. That's why we spent so much energy working with the explicit formulas, is because they continue to work. What we need to work on is, think about this. Everything starts at 100%, which is not a number. Remember, 100% is not a number. It's a representation of the number 1. Everything is based on 100%. How close are we to 100%? How much higher, how much lower have we changed? But don't think about starting at 0. Think about starting at 1. We're either going to increase by moving up or decrease by moving down. Good news on the down, you can't get lower than 0. All right, so let's talk about this. It says Lisa purchases a house for $140,000 near Lake Jackson. The value of the house in the areas purchased are increasing by 4% per year. And then we've got several questions that follow this. Let's first talk about this. A sub 1 is pretty easy. The house is starting at $140,000. The rate of change is 4% increase, but here's what I'm talking about on the 100. Lisa doesn't want 4% is 0.04. Lisa doesn't want 4% of her house value. She wants 104%. So our rate is 1.04. because she has increased. Increased from what? Increased from 100. All right, so that we've actually answered our first question. What would be the growth factor, the multiplier? Our growth factor would be 1.04. If the trend continues, how much would the house be worth 12 years after the loan? Always pay very close attention on this. So let's set up our formula first of all. That's our starting amount. That's our rate of change. And then it's going to be t minus 1. I'm just using t because they said to. Now, think about this. It says, what would Lisa's house be worth 12 years after? Well, 12 years after would be the 13th year. A lot of times what you want to do on these things is look at the calculator. I actually put this in the y equals. And I just take a look and see how much the thing is worth and make sure that it matches. But if we're talking about 12 years after, that is the 13th year because we have this equation set up to measure the value at the year. So you can go back and look at your calculator. If you put this into your y equals, it's a very smart move. And if you look, it will have the ordered pair 1,140,000. That is our x and our y value. So we're looking for the 13th year. All right, this is B, by the way. There's our equation. So after this would be the 13th year because it says after 12. After 12 is 13. So the value of Lisa's house would be $224,145. And I have already put that in my calculator. If you thought I did that in my head, I appreciate that, but not quite that good. Remember, you would plug in for t the number 13, because 12 years after is the 13th year. You've got to pay attention to how you have your equation set up. All right, building off of that, Esther purchased a car, a Ford Focus, for $8,500. The purchase is the car is expected to decrease in value by 15% each year. But again, we always start at 100%. So if it's depreciating, it's losing 15%. And remember, 100% is not a number. It's a representation of the number 1. So if we subtract 15%, that would be 0.85, and that's our rate. Her car will be worth 0.85% of what it was. All right? What would be the decay factor? We just talked about that, 0.85. That's what our common ratio is going to be. If the trend continues, well, let's create our equation. This is geometric because it is a multiplication pattern. So her car started at $8,500. It will be retain 85% of its value over time minus the 1 year. So this is actually the equation. My equation's technically wrong because the instructions say call it VT, value over time. So I'm going to make that change. And then if the trend continues, what would it be worth 6 years after? Well, 6 years after would be the 7th year. I've already taken this and put it in my calculator. So all I've got to do, you can do the same or you can trust me. I look at this and I see year 1, Ford Focus is worth $8,500. So after 6 years, that would be 6 years after year 1 is year 7. So what we end up with is a car that is worth $3,200, excuse me, $5.80. That's called depreciation. Something that loses value depreciates. Anything that gains value is appreciation. Some of you have probably dealt with this with personal finance. Remember, it's all based on 1. We start at 100%. All right, here is a real tricky one. Not that it's very difficult, it's just you've got to pay attention to your unit of measurements. This is a lot like your science ACT, things of this nature will pop up. But here we go. says Jade is currently getting paid $7 an hour. That sounds like a sub 1 to me. I don't know about you. Starting amount. Here we go, 6 months she works there, she'll get a 50-cent raise. Well, that sounds like a difference, doesn't it? So we have our two elements here. How is her pay changing? 50 cents. We're just going to write this down. 50 cents per 6 months. Twice a year, right? We could also set it up that way, but it asks for 65 months. So we probably want to put this in this. And this is an interval question. So it's not like she gets it every month. After the 6 months, she gets the raise. So we're going to have to talk about this. If she trend continued, how much would she get paid after the 65th month? All right, we'll worry about that in a second. Let's write the equation. Here's the important thing when writing the equation. Writing the equation's easy. A sub 1 plus the common difference times the n minus 1. And let's see, we're actually using m as our variable, months. I'm going to put a note to myself anytime I do these, though. She's not getting a raise the first month. That's why we have to subtract 1. I'm going to put a note to myself here and make sure I see this. M stands for 6 months. 6 months. All right. So the important thing here now is to see how many 6-month intervals we have had. I cannot just plug in 65 here because I noted to myself that, hey, M stands for 6 months. So what I'm asking myself, what I'm asking you, is how many 6-month intervals are there in 65 months? So we have 65 months, 6-month intervals. We would actually get a decimal. We would have 10 full month intervals, and then we will have a decimal, won't we? But we did not get the next pay bump. I don't care if this number rounds up. Let's actually see what the number is. We're doing 65 divided by 6. The number is actually 10.83. Well, that number rounds up. Yes, but that's not how she's getting paid. Every 6 months, so she's only had 10 6-month intervals. So that will be our plug-in value. She's had 10. Whoops. But we have to minus 1 because they don't give her that pay. They don't give her that pay for the first 6 months. She's got her $7. So she will have gotten a boost of 50 cents 9 times. She's had 10 6-month intervals. The first one is not a pay boost. From then on is. So she would get 9 50-cent pay raises. So she's getting paid $4.50 more, taking to her to $11.50. Very important you read your question. Make sure I did. It says, how much would she get paid during, not after. That's why I didn't do 66. It says during her 65 month. So she would only get paid, she would get about a $4.50 raise over that period of time, and she would make $11.50. It says write an equation for the numbers per month. Really, to be honest with you, due to the intervals, we want to leave that in a 6 month. Just make sure you make a note to yourself. Technically, if it asks for in months, you'd have to do months divided by 6 because we are dividing the ratio up. All right, I'm going to pick up the pace a good bit here. It says determine whether these are linear or exponential. I might as well, this is what I was talking about at the beginning. When I say linear, I might as well be saying arithmetic. When I say exponential, I might as well be saying geometric. It's all phrasing. It's all phrasing. So we need to ask, do we have a common ratio or a common difference. All right, so in this one, we do have a common ratio. We have a common ratio. Again, I'm going to pick up the pace a good bit here. This is increasing by 1/2 each step of the way. The way we can get this is you just take the term minus the previous term. So we have a common difference of d on this one, 1/2, excuse me, positive 1/2. Now, a sub 1, make sure you don't use 0. Remember, we start with our first term in the sequence. So a sub 1 is 3/4. So if we were going to write this equation, we are starting at 3/4. We are changing by 1/2 times n minus 1. If you don't see this formula, if you do not see this formula, distribute and solve. Some of you may have done the y equals mx plus b. That's fine. Knowing our change is 1/2, it's all going to work out the same. All right, on the next one, remember, we can't do this math in our head, so what we're going to do is just divide by the previous term. So 6 divided by 7.5 is 0.8. I can clearly see that's not an adding change. I'm actually going to jump all the way to the back, make a little assumption, a lot like you guys do. We don't plug those all in all the time. Let's just see, just a little spot check here. And I divide this one, and this is also 0.8. So when I'm writing this equation, I'm going to write it as a sequence. We started at 6. Write this down here. A sub 1 is 6. And our ratio is 0.8. So starting at 6, ratio of 0.8. N minus 1. N minus 1. Guys, there's actually an infinite number of equations we could construct here. I'll show you the other one that you're probably going to see. That would be just backing the pattern up one. Well, if I back the pattern up one, we would be sitting at 7.5. The ratio would be the same, and now it would not be n minus 1. It would just be normal n. If you were to put this equation or this equation in your calculator, you're going to get exactly the same thing because they are exactly the same thing. All right, if you've noticed, I skipped a section. I'm going to do that on the video, but this will not be on the test, but I'll put it on there. If you're curious, you'll be able to look at those. All right, these two should go really quickly. Again, this is just me pointing out some verbiage to you. A and B, A on an exponential equation is the same thing as saying A sub 1. B is the same thing as saying common ratio. Starting point and the base of the equation. So this is the A value, this is the B value. Again, when we're talking about exponentials, it's just a different name. A sub 1, and then this is our common ratio. Now it's technically not A sub 1 because it is normal x, but the idea is the same. The idea is the same. This pattern is backed up one from a sequence, but here we go. It says identify the A. Well, A we already talked about. A is 4,000. B is 1.25. Now, what this means is whatever we are talking about starts with a value of 4,000. I don't know what we're talking about. I don't know if we're talking about energy, car price. It really doesn't matter what we're talking about. We just know this has a value of 4,000. And then we look and see that our B value is greater than 1. Anytime you have value greater than 1, it's growth. And however much greater it is than 1 is its percentage of growth. So we're talking about 0.25. which is equal to 25%. So whatever this is experiencing a 25% growth, exponential growth. So that's what we would note as our terms there. Whatever it is, started at 4,000. Whatever it is, it's growing at a rate of 25%. All right, let's do the same thing with the second one. The A value is our value not attached to the exponent. So this is $100. It could be dollars, who knows. Our base value is 0.77. So this value is less than 1. Let's talk about this first of all. Whatever we're doing, we're starting at 100. I don't know if it's dollars, heart rate, whatever it is, it's starting at 100. Whatever it is has a rate of 0.77. It's 77% of what it should be. Well, 77 is 23% lower than what it should be. It's supposed to be 100%, but it's 23% lower than what it should be, also known as a decrease. So whatever this is experiencing a 23% decrease from its initial starting value of 100. So this is how we recognize these based on those pictures, or this information.